This is AP Calculus BC, and in this video, I'm going to talk about parametrics and vector calculus. So what we're really doing in this section is we're transitioning from working with parametric equations like we did in the last class, and we're going to start working with actual vectors. And if you remember, I told you what we're trying to really do here is get to the point that we're transitioning into 2D vectors so that you can then take the next step. If you're going to take, for example, a Calculus 3 course, you can get into three-dimensional vector calculus, which really opens up a lot more possibilities from the standpoint of applications for all of our calculus concepts. So as we go through this, there's a lot of just common terminology about vectors that I'm going to be using and that you're going to need to know. Now, these are things that you've seen before in pre-cal. You've probably seen them in your physics classes. So a lot of this will be familiar, but just keep in mind, since we're now dealing with vectors, the way we refer to things, the way we write things, some of those things are going to change a little bit. So what I've included here is just a list of some of the common terminology and some of the common calculations that we do with vectors. So remember, a vector has magnitude and direction. And how this relates to what we were doing with parametrics. Remember, with parametrics, we were getting an equation for x in terms of t and an equation for y in terms of t. Well, now we're just going to essentially display that in vector form. So it's a really easy transition back and forth between parametric form and vector form. Remember, the magnitude of a vector is just essentially the length of the vector. So there's a lot of different things here. When we add vectors together, we just add the corresponding components. When we subtract vectors, we subtract the corresponding components. When we multiply by a scalar, we multiply every component by that same value. We'll talk a little bit about position vectors and velocity vectors as we get into some of the applications of vectors. So the big thing here that we're going to see a lot of is when we start to get into these components. So the unit vectors I and j. So remember, I is just a vector that points in the horizontal direction, and that vector has a length of 1. That's what makes it a unit vector. J points in the vertical direction and again has a length of 1. Okay, so when we talk about the components of a vector, there's a lot of different notation we can use, and we're going to go through that a little bit. But this is one notation we can use for vectors. See how I have the V with the arrow over the top? That is telling me my vector in the I direction is x times I and y times j. In addition to that, sometimes you'll see this written with a half arrow like this. So xi plus yj. Sometimes you'll just see it written in bracket form. And when we write it in bracket form, it's just going to look like this. Usually vectors are used, or angle brackets are used for vectors. And we would just write it like this, and we go in order here. So that would be x in the I direction, y in the j direction. And then if we had to go in a third dimension, we would just add in, let's say z, and that would be our k component. So again, we're only going to focus on 2 dimensions, but it's very easy to work in extra dimensions as you move forward with this. Okay, so in addition to that, we do have some information here about dot product, which you did a little bit of in pre-cal. And primarily for us, what we're going to be thinking about with dot product is finding the angle between 2 vectors. Sometimes this is called the inner product or the scalar product. But for us, we're really going to be limited in the applications that we do. But one of the main things we're going to do is find the angle between a velocity vector and an acceleration vector. And the big thing you need to know when you find a dot product is it has a relationship to the angle between the 2 vectors. And if we get a positive dot product, that means that angle is acute. If we get a dot product of 0, that means that angle is 90. That means those vectors are perpendicular. And if we get a negative dot product, that means that the angle between the 2 vectors is greater than 90. Okay, so let's just go through a really quick review of finding a dot product. So this is really easy to do. When I find a dot product, like here, they're talking about vector 1 and vector 2. When I find the dot product of 2 vectors, this is the notation that I use for dot product. It's just essentially like a closed-in circle there. It's just a dot. And when I find the dot product between here, vector 1 and vector 2, all I'm going to do is multiply the corresponding components together. So in this case, it would be 3 times 6 because those are the I components. And then I'm going to multiply 1 times 6 because those are the j components. And in the end here, I get 24. Now, remember, that has a relationship to the angle. That dot product is equal to the cosine of the angle multiplied by the magnitude of vector 1 times the magnitude of vector 2. Well, they didn't ask us to find the angle. They just said here, is the angle between the vectors acute or obtuse? I got a positive value, so that tells me that the angle is acute. Remember, if you get a negative value, that means that your angle is going to be obtuse. Okay, so now here's just an example. I'm not going to go through all these calculations, but this is what a lot of what you're going to see when we just do a little review of vectors. So all they're asking you to do here is they're giving you some vectors and saying, okay, given these vectors, perform these operations. You can see we're adding, we're subtracting, we're multiplying by scalars. Here, when you see this notation, that's finding the magnitude of the vector. So if I want to find the magnitude of vector A, that's just going to be the square root. Just think of it as the Pythagorean theorem. So I'm going to do 1 squared plus 2 squared. So the magnitude of vector A would be square root of 5. That's the length of that vector. So remember, we're just thinking of it as a right triangle. The I component is one leg. The J component is another leg, and then just find the hypotenuse. Okay, so very simple. When you see this notation, that's telling me it's a unit vector in the direction of vector A. So what that means is I'm pointing in the direction of vector A, but now I'm just going to use a magnitude of 1. So it becomes a direction vector. So that's how we really use those unit vectors, is when we need to have something point in a certain direction, then we can have a vector that points in that direction. We can turn it into a unit vector and then multiply by whatever scalar we need given the circumstances. Okay, so anyway, there's a lot of calculations there. We're not going to go through all of them because those are all things that you've done. They're all fairly simple. But remember with magnitude, how those are calculated. Remember what a unit vector means. Okay, so here's some of the notations that you might see. Talked about this a little bit already, but you can see the angle notation here. Now, here's the thing. When we're looking at this vector notation like this one, that's telling me that x is equal to t squared minus 2t, right? Okay, so let's talk about vector notation. And you can see here, I've got this written in this angle notation like we talked about a little bit earlier, the angle brackets. And all this is really telling me is that's the parametric form, right? My x is a function of t and my y is a function of t. So the parametric form and the vector form are almost interchangeable. We can also write this where we have it written out component by component. And you can see here t squared minus 2ti plus t plus 1j. I can also use, you can see the arrows here are the full arrows. Here I've got the half arrow. We also have the bolded letters I and the bolded letter J. Now the problem with that is when we write these out by hand, it's very hard to indicate that something's bolded. So this is something you'll see in print a lot, but typically when we write it out, we don't really write out a bolded I and a bolded J. We usually use the arrow or the half arrow or the angle brackets. Okay, so a vector equation of a line. So we have a lot of different ways that we can represent the equation of a line. We can do it in just our typical rectangular form, y is a function of x. We can do it in a parametric form, and we can do it in a vector form. When we do it in a vector form, we're essentially doing the process of creating a position vector. So what the equation of the line represents is for any value of our parameter, where does the vector from the origin point? And that takes us to that position. So in this case, you can see our vector equation of our line, r is equal to the initial vector, that's like our initial value, plus t times v, where v is our direction vector. So we're going to find the equation of a line here in a second, but that's just a reminder of how that works. So here it says find the vector, parametric, and Cartesian equations of the line that passes through the points 3, -2, and 5, 7. Okay, so this is actually fairly simple to do. We'll start with the vector equation here. So when we do this vector equation, what we're going to do, first of all, is we need to know what's our direction vector. So let's do our vector equation of the line here. We know we're typically going to use r of t for that equation. So we need our initial point. We started at the point 3, -2. So that's a position. From the origin, we're pointing to 3, -2. And then to move along that line, we want to move in the direction of the line. And what we do is we do our parameter times our direction vector. And our direction vector is just how did we change to get from one point to the next. We moved 2 units in the I direction, and we moved 9 units in the J direction. And all I did here was I looked at these components, it went up by 2. And then for these 2 components, we went up by 9. So that's all I did. Okay, so vector equation is very easy. To go now to a parametric form, all I have to do is know how to read this vector form. So just look at the I components. Those are the X parts of this. So for the X piece of this, I have 3 and 2t. So that means my parametric form would be 3 plus 2t for the X. And then for the Y, I'm going to have -2 plus 9t. Okay, so again, really easy to go back and forth. Now for the Cartesian form, that's just where we have y as a function of x. We have to have y in terms of x, right? So now we have to think of how do we find the slope of the line, find the slope between the 2 points. There's a relationship here I'll show you in a second, but we do y minus y1. So in this case, I'll use a as my initial point. Y plus 2 is equal to my slope, which the change in y over the change in x would be 9/2 times x minus 3. So all 3 of these are displaying the same information, just in slightly different ways. And if you notice here, my slope of 9/2 actually shows up here. I can see my y direction was 9, my x direction was 2. So the y over the x gives me 9/2. So that slope matches up. Okay, so again, really easy to do. A lot of this is just review as you go through this. Okay, so now let's get into the calculus part of this. So we can take derivatives and integrals of vectors very easily because we just go component by component. And that's what we're showing here is if I've got some vector, typically it's going to be a position vector, and I take the derivative, I just do the derivative one component at a time. Okay, so here's an example. We've got r of t is 1 plus t cubed I plus t e to the negative tj. So to get the derivative of the I component, it's just 3t squared in the I direction. And then for the j component, it would just be e to the negative t minus t e to the negative t in the j direction. So all I did there was the product rule. And now I've got my derivative of my vector, so the r prime vector. Okay, so again, really, really easy because we're just going component by component. In a lot of ways, when we work in component form or vector form or parametric form, however you want to refer to it, it's easier than what we did when we had y in terms of x because we're separating the x and the y out into very, very easy to work with equations typically. Okay, so also we can do the same thing with integrals. We can integrate term by term. Here you can see we're integrating. So if you want to think of why would I ever do this? If you think of this as a velocity vector, let's say r of t is the velocity. If I were to integrate a velocity vector, I would get the displacement. So here what we're doing is we're integrating the components one at a time. Okay, so for example here, we've got one that we're going to solve out. We've got the integral from 0 to 1. And you can see the vector 16t cubed I minus 9t squared j. So what I'm thinking about here is just setting this up as 2 separate integrals. So I've got that all multiplied to my I plus, or really in this case, it'll be minus the integral from 0 to 1 of 9t squared dt. And that will also all be multiplied to my j. Okay, so just integrate one component at a time. In the end here, if you were to solve that out, you'd get 4i minus 3j. Okay, so for today, that's going to be our primary focus is just kind of those basic ideas of working with vectors. And what we're going to focus on next time is we're going to start getting into some really simple applications, which primarily we're just going to do motion problems with vectors. But again, keeping in mind the grand scheme of things, the purpose of all of this is we want to start thinking about our calculus in a vector form so that we can then expand our calculus into 3 dimensions. Okay, at the end of this packet, I do have a worksheet here for you. So this is really what I want you to do for homework. And keep in mind as you work through this, there's going to be some simple motion problems in here, but we'll get into more complicated motion problems next time.